We're going to spend a couple of videos looking at both cardiovascular and respiratory responses to exercise. Mainly it'll be cardiovascular responses, and we're going to look at submaximal, prolonged, and incremental exercise. So I want you to try to look at some of these figures and understand what's going on. And so as you look at this one, you should say, well, the y-axis is cardiac output, and I can see that cardiac output is increasing and then plateauing. And so you should be saying to yourself that this is submaximal steady state exercise. And I know that that's what's going on here. Well, why is it that cardiac output would increase during exercise? And this should make a lot of sense to you. Well, the muscles are working harder and they need more final electron acceptor. That means that the heart needs to pump more blood to those muscles. Well, what's the underlying cause of the increase in cardiac output? And again, you should remember that cardiac output is stroke volume multiplied times heart rate. And so not surprisingly, the stroke volume is also going to go up as the person begins to exercise. Now you can see that the change isn't as great, but the pattern of response is really the same. So we get a fairly quick increase, but then a slower increase, and finally we hit the steady state plateau that you see here. And notice that the units aren't quite right. They should be stroke volume in milliliters per beat, and we start at roughly 70 milliliters per beat and go up to about 110 milliliters per beat. Well, you also know that heart rate will go up, and again you can see that the pattern of response is exactly the same. This person's resting heart rate looks to be about 70, and it's increased up to about 140 beats per minute. And so again, those two things help to account for the increase that we see in cardiac output with submaximal steady state exercise. We know it's steady state because of the plateau that we see here. Well, look at the blood pressure data and see what you think about this. And one of the things you should notice immediately is that during aerobic exercise, it appears that diastolic blood pressure doesn't change. And that's true when we look at the average of people. If we looked at one person, we might find a slight increase in diastolic pressure. In another person, we might find a slight decrease in diastolic blood pressure. Most people show no change. And so when we average all of that, we just see kind of a constant DBP. Not surprisingly, systolic blood pressure is going up. The heart's pumping more blood into the system. More blood in the system means higher blood pressure. And so that's what's going on. And we see the increase during the heartbeat, systole, but not during when the ventricle is relaxing, diastole. Well, think about what you'd expect for RPP and for TPR. And you should remember that RPP is the rate pressure product, or the heart rate times the systolic blood pressure. Well, you saw that heart rate went up. You see that systolic blood pressure goes up, and so RPP too has to go up. And again, it goes up fairly quickly. And I meant to point out to you, and I'll point it out here, you go back and you look at these things, and again, they reach the plateau in under 5 minutes. So keep that in mind. And then because these numbers could get so large, what we do is we take that heart rate times systolic blood pressure, divide by 100, and so that keeps the numbers on the y-axis a little bit smaller and a little bit more manageable. Well, here you can see the peripheral resistance. So again, TPR, and you can see that TPR is decreasing quite a bit. And that's because of the vasodilation of the arterioles into the exercising muscles. Resistance is proportional to the length of the vessels times the blood viscosity divided by the radius raised to the fourth. And so that means that a small increase in the vessel diameter is going to result in a fairly substantial decrease in resistance to blood flow. And that's exactly what we see. But again, we seem to hit a steady state in 5 minutes or less for this. And that's true for all of these variables that we've looked at. These pie charts, which we don't use a whole lot in exercise physiology, are showing you blood flow distribution. Here you can see that the total of all of these is the cardiac output. This is a fairly big person. 5.8 liters per minute means that they're a little bit bigger than the average individual. And you can see here that the muscle is only getting about 20% of the blood flow, and the liver is getting more than that, and the kidneys are getting about the same amount. Well, when we go to exercise, and this isn't real strenuous exercise, cardiac output is less than 10 liters per minute, you can see a really big increase in blood flow that's being directed to the skeletal muscles. And again, that's because of lots of vasodilation of the arterioles that are bringing blood into those skeletal muscles. You might also notice that there's an increase in blood flow to the cutaneous blood vessels, and this is to help you cool yourself, and so more warm blood can come out towards the surface of the skin and radiate heat away. And so that's what that is all about. This chart is just, again, trying to help you understand what some of these changes are due to, and most of it is due to the increased activity in the sympathetic nervous system. So you know that's going to make the heart beat faster and harder. That's going to contribute to the vasodilation of those arterioles to the skeletal muscle, but at the same time, it helps to cause some vasoconstriction of the arterioles that go to the organs of digestion, the liver, the kidneys, the large intestine, small intestine, and so on. But then as the muscle is working hard, it's building up these metabolites. I didn't want to do that. And those metabolites can also act on the smooth muscle and the arterioles going to these working muscles, which also helps to cause this vasodilation. So even if we were able to block the sympathetic output, we'd still get vasodilation of blood vessels to the skeletal muscle because of these metabolites that build up here. Well, now what's going on? What's different here? Number one, you might say, well, the person's working harder because the cardiac output is higher. The person is also doing prolonged exercise because now they're continuing for greater than about 35 minutes. But again, notice that we still reach this plateau in about 10 minutes, even though it is going about 4 times higher than resting. And you'll notice that we still see a steady state here. But now when we look at the stroke volume, oh, look at that. You actually see that after about 35 minutes, stroke volume starts to creep down. And that, again, is what we refer to as a negative drift. Well, the only way that we could keep cardiac output constant in this case is if heart rate shows a positive drift, and that's exactly what happens. And so again, at about 35 minutes roughly, the heart rate starts to creep upwards, and if we had this person exercise long enough, we would actually hit their maximum heart rate. And you can see that this person is starting to get close to it. Okay, well, a question is, and I hope you maybe thought of this, why is stroke volume decreasing? And again, I want to remind you that stroke volume is milliliters per beat, not milliliters, and so I need to take some points off of the person who made that graph. And the reason for it is because of what's referred to as a fluid shift. That's what's going on here. And so the fluid shift is due to these Starling forces, which we talked about in anatomy and physiology. And so as the blood moves into the leaky capillary, there's a hydrostatic pressure. That's this pressure of the fluid pushing against the capillary trying to escape. And since the capillary is indeed leaky, fluid does escape. Over the course of a day, you push 24 liters of fluid out here. Well, you've only got 5 liters of blood, so that's a lot. Well, you can see as we move across to this side, the hydrostatic pressure has decreased considerably, but on the other hand, the osmotic pressure has increased, and that means that most of that fluid is reabsorbed. And so you can see of the 24 liters, 20.4 were reabsorbed. And so the Starling forces are the hydrostatic pressure trying to push fluid out into the interstitial space, and the osmotic pressure that's trying to bring the fluid back in. And that's exactly what happens. On the arterial end of the capillary, fluid leaves. on the venous end of the capillary, fluid returns. So we can see what's going on. This is just showing you an enlarged view of the endothelium. And again, there is space in between these endothelial cells, and so lots of fluid will get out and escape. But you can see that we do have these large proteins. They're too big to get across, and they remain behind. And that's why the osmotic pressure on this side is increasing, trying to pull fluid back into the system. Some of the smaller proteins do escape. Now, what they're not showing you here that don't get out would be the red blood cells and also the even larger white blood cells. And so large proteins, blood cells cannot cross the endothelium. So the stroke volume is decreasing because during exercise we have an increase in blood pressure. That increase in blood pressure causes an increase in the hydrostatic pressure. Again, this is the force of the blood against the leaky capillary. That pushes fluid out into the interstitial space, and this is what's known as that fluid shift. Because fluid is being pushed out, well, now you have less blood. Less blood means smaller venous return. Smaller venous return means a decrease in end diastolic volume. And again, you know that stroke volume is directly related to end diastolic volume. If end diastolic volume goes down, stroke volume goes down. If blood fluid level goes down, EDV goes down. And so that helps to explain it. And here you can see that change in plasma volume over 30 minutes of exercise. And the majority of the fluid is leaving the capillary space within the first 10 to 12 minutes of exercise. And then a bit more will leave after that. But again, net result is negative drift in stroke volume. Negative drift in stroke volume. Here are the blood pressures again. Hard to see here, but there actually is a little bit of a negative drift for the systolic blood pressure. Again, less blood pressure. DBP seems to stay about the same because it's when the ventricle is relaxing. Well, RPP still goes up. And the fact that we have positive drift means that the drift in heart rate more than compensates for the negative drift in systolic blood pressure. And again, RPP is heart rate times systolic blood pressure divided by 100. And then, not surprisingly, the peripheral resistance is going down. And again, that's because of the vasodilation of the arterioles to the muscles, causing an increase in radius. And you know that the resistance to blood flow is directly related to the radius. The bigger the radius, the less the resistance. And here again, we can see distribution. Again, this is rest, and now this is heavy exercise. It's not maximal, but it's getting up near 20 liters per minute, and so the person is working pretty hard. And now there's been a tenfold increase in the amount of blood going to the skeletal muscles. At rest, it was 1.2 liters. Now it's 12.5 liters. And so that is accounted for by all of the vasodilation that's occurring in those arterioles feeding the skeletal muscles. Skin blood flow is still higher than it was before. Again, trying to help with cooling of the body. Well, here you can see cardiac output and how it changes relative to incremental exercise. And so the person is starting at rest, and then they work harder and harder and harder, as we did in our incremental tests that Nathan and that Andrea did, and also as you did in Intro to Kinesiology to do your max tests. And here you can see cardiac output is increasing from a resting value of about 5 for this individual up to just under 25 liters per minute. Here you can actually see adaptations in the response of cardiac output to, again, incremental exercise. Now it's absolute values because it's liters per minute and not percent of maximum. The yellow is sedentary college students. The greenish is those same students after they've done a couple of months of training. The arrows that you see here indicate the time where the individual said, that's it, I can't go any further. And so you can see that there's a really nice big increase in Qmax for these endurance athletes compared even to the trained sedentary people. But even they had a bit of an increase in Qmax, so it did go up some. And then here's just a slightly different way of looking at the blood flow distribution during incremental exercise for cardiac output. And you can see that the major thing is lots and lots and lots of that cardiac output is being directed to those skeletal muscles. The other thing that you might notice is, look right here. As we approach maximum, blood flow to the skin starts to decrease. And what the body is saying is, all right, right now, it's more important that we get final electron acceptor to these skeletal muscles, and cooling the body is going to have to take a back seat. A number of people believe that this is the major limiting factor in a person's ability to push themselves during endurance exercise. They can't tolerate the increase in core temperature, and so they fatigue sooner than somebody who can tolerate that increase in core temperature. Well, here we see the change in heart rate with incremental exercise. In this particular case, they're showing that the heart rate plateaus a little bit as we get up over 90% of VO2 max. The truth is that not everybody shows that plateau, but a few people will. And again, here you can see the adaptation in heart rate, and you can see that it still goes up a little bit here, but it does go up more slowly. So it's not quite a plateau, but it is kind of plateauing a bit. And you understand that resting heart rate decreases, and it decreases more for the endurance athlete. Submaximal exercise heart rate has decreased. The other thing that you need to pay attention to, look, with enough training, even maximal heart rate decreases. The maximal heart rate of the endurance athletes is 180 beats per minute. For the sedentary college students, it looks to be approximately 190 beats per minute. Now, it doesn't look like there's a significant decrease for these college students, but if they continued to train for a couple of more months, we would see the maximum heart rate start to go down some. So all heart rates go down: rest, submaximal, maximal exercise. And then here you can see the change in stroke volume for incremental exercise. Now you got to notice, oh, look at that. When we reach somewhere around 50 to 60% of VO2 max, stroke volume doesn't go up anymore for these people. Not really a steady state. They've just reached their maximum capacity for stroke volume, up around 130 milliliters per beat. Milliliters per beat. I don't know if I can write this in. I'm going to try it. Milliliters per beat. Well, that's not too bad. Okay. Here is some other data that shows you basically the same thing, but you see here that the stroke volume is continuing to crawl up a little bit. It hasn't really plateaued until we get up over 75% of VO2 max, but it does indeed plateau. This person, you can see their resting stroke volume looked to be about 68 milliliters per beat. Oh, yay, they got the units right. Up to almost 120, maybe around 115 milliliters per heartbeat. Some more recent data suggests that elite trained people only start to slow down their increase in stroke volume, but it doesn't really plateau. These guys are continuing to go up, and these are some absolutely huge stroke volumes. Over 180 milliliters per beat, right? Milliliters per beat. Don't get it wrong on the test. And that just is an astounding stroke volume to have. So really, really, really high there. And again, I want you to understand that these aren't just highly trained. These are elite. And so these are the guys who are hoping to be running in Japan this summer. We'll have to wait and see what coronavirus does to the Olympics for the summer. Here you can see some similar data. And so the red is untrained, and then the blue is that same group of people after training for a few months. That's interesting right there. And so maybe even these people who aren't quite elite can continue to push their stroke volume some. But look, they hit a max of about 140. And again, these guys over 180. That's pretty phenomenal. This actually shows you stroke volume. And so the top line, as you can imagine, is really the EDV. That's what we have here, the end diastolic volume. And the bottom line is the ESV, the end systolic volume. And you know stroke volume is the difference between those two. So stroke volume is EDV minus ESV. And you can see that EDV goes up quite a bit. This is just left ventricular end diastolic volume. They don't need it because EDV has to be pretty much the same. Whatever happens on the right side happens on the left side. And so LV EDV is going to be approximately equal to RV EDV, and the same for end systolic volume. And so you can see again, as we go from rest to moderate exercise, there is a fairly big increase in EDV, largely because of muscle pump, respiratory pump, and reflex venoconstriction. And there is a little bit of a decrease in ESV because the sympathetic nervous system is making the heart beat harder. It's beating harder. Okay. Here we can see blood pressures for incremental exercise, and the systolic blood pressure can indeed get up around 220 millimeters of mercury, so nice and high. But it's still aerobic activity, and so the DBP is remaining relatively constant here. And so again, the RPP gets really high values, but again, it's heart rate times systolic blood pressure divided by 100 to keep these values on the y-axis from being 100,000 to 400,000. And there does tend to be a little bit of a plateau up here. You can see that plateau there. And some people do have a plateau in heart rate as it goes up. And then resistance drops down quite a bit. We've gotten maximum vasodilation of skeletal muscle arterioles, and so resistance has dropped down so that it's under 5 resistance units, And then again, here's blood flow distribution. And now the blood flow to the skeletal muscles has just increased a huge amount. It's over 22 liters per minute. That's a lot of blood. That's like 11 2-liter Coke bottles filled up with blood, and they're filled up in 1 minute. And now look what happens to skin blood flow. And so again, the body is saying we've got to sacrifice cooling to get the blood to the muscles so that they have the final electron acceptor they need. And that's part of the reason that you would only be able to keep up this level of exercise for a few minutes at the most, because you are indeed going to overheat as you do that. These data just show a comparison between lower body and upper body exercise, and you can see that Q is roughly the same. The stroke volume for upper body exercise is actually less than the stroke volume for lower body exercise, and that's because less of a muscle pump. Less muscle mass, less muscle pump, the venous return won't go as high. In order to try to make up for that, the heart rate has to be higher during upper body exercise. And if you're working with a person who has cardiovascular disease, you have to know that, because the same exercise intensity can push the heart rate to a higher level, which might stimulate a heart attack in this person. So if they normally do lower body exercise and they switch to upper body, you need to decrease the exercise intensity so that you don't kill them. To keep at the same heart rate, you need to come down some. All right? And so again, stroke volume is lower because of less muscle pump. Well, you can also see that the upper body exercise results in a higher blood pressure. And so the question might be, why is that? We're not positive, but it seems to be that the sympathetic nervous system is more highly activated for the upper body exercise. And that's what results in the greater increase in blood pressure here. And so at a given VO2, you have a higher blood pressure for the upper body exercise than you do for the lower body exercise. And then here you can see, again, since blood pressure and heart rate are higher, RPP will be higher. And again, RPP is a reflection of how hard the heart is working. So higher RPP, the heart's working harder, and it is more dangerous for somebody who has underlying cardiovascular disease. And then finally, here's the resistance to blood flow. More blood vessels in the leg muscles, more arterioles, greater vasodilation, greater decrease in resistance. And so there's the TPR. And that brings us to the end of this video. And in the next video, we'll finish up a few more things on cardiovascular responses, and then we'll talk about a few respiratory responses, but not many.